We started before the previous class. So we have seen what is, how thermal energy is generated during machining. There are three zones. In those three zones, so heat will be generated. So most of the power or the power, I will say, most of the power we are using for machining operation is finally converted to the temperature or heat. So that heat is okay, not desirable for the workpiece and for the tool, because it will okay, for tool, let us say, it may distort the tool, okay, or thermal cracking may be there, etc. For workpiece, the surface microstructure may change, okay, it may be burnt, surface may be burnt, etc. Some scaling may form, oxidation. So it is undesirable. So you want to reduce the temperature. You have seen the different methods, mainly cutting fluid application. And of course, we have seen how to estimate the temperature at the shear zone and chip and tool interaction zone. Okay, there are various methods, analytical method and some experimental equations derived from experiments and dimension analysis. So all those methods we have seen, and we have seen experimentally how you will do that by using thermocouple method. Okay, you can use the embedded thermocouple method also, radiation method, micro hardness method, and different methods are there. So we have discussed all those, and we have seen one numerical problem related to thermal aspects. Now the next topic is tool wear, tool life, and machinability. Now let us start. I request the CR to record this. This is the topic: tool wear, tool life, and machinability. Now tool wear. So all these are interrelated. Mainly tool life and tool wear are very much linked together. Okay. Generally, in machining, tool fails due to gradual wear. Generally, sometimes tool may break suddenly, that is a catastrophic failure, or tool may deform, or tool may bend, etc. So that is also tool failure, but that is not the desired method for the tool to fail. So we tool will anyhow invariably it will fail after some time. So but we want tool to fail gradually, or the due to wear tool should fail, not because of a sudden breakage, not because of sudden bending, etc. Okay. So tool wears gradually. So due to that, after some time, tool may become blunt, okay, or it may become very weak. So and it will not give required dimensions, okay, for the given parameters, etc. Then we will say tool has failed. So that method of tool failure is desirable. Okay, if tool suddenly breaks during machining process, so then it may just fly and hit the worker, or there will be sudden change in the force, and the machine may also get damaged, etc. So that is not desirable. Okay, now let us try to understand what is this tool wear. First point is consequences of tool wear. So if tool wears out gradually, what may happen during machining? So one thing is large power consumption. So initially we'll have very sharp cutting edge. Now tool is worn out after some time. So it may be a little bit rounded off, okay, or some curvature has come. So it is not sharp. So obviously you need more power for cutting the material. Second, it affects the dimensional accuracy. Again, if your tool has become blunt, okay, you will not get the exact dimensions that you intend, okay, for a component which is being cut. Another thing is deteriorated surface finish, okay, because now the tool tip is no longer sharp. So material is not okay simply removed. Okay, you are exerting very heavy amount of force, etc. So surface finish will be poor. Okay, so there will be more compression. Okay, more amount of compression is there, and of course, a built-up edge will also come into picture if tool is not sharp. And overheating of the tool. This is also obvious because tool is blunt. You are giving more energy to remove the material. So there is more interaction force between the workpiece and tool, which will obviously result in increase in temperature. Now shortens the tool life. If the tool is worn out, obviously tool life will go down because our tool is not giving the intended performance. So if tool is not giving that intended result or performance, then we will say that tool has failed. Okay, it need not break physically. If it is not giving the desired machining characteristics, so tool is failed. Now it generates chatter vibrations. So initially tool has some size. Now due to gradual wear, there will be some minor changes in the dimensions of the cutting tool. Okay. So initially tool is something like this. Now it has worn out. Okay, its length has changed. Maybe in some okay very minute dimensions, let us say 0.5 mm. But still there is a change. So due to that, this engagement, okay, there is now difference, 0.5 mm difference. So tool may now, okay, it will move in this fashion. Okay, oscillating motion that will lead to vibrations and chatter. And of course, some more cutting force is also coming onto tool, so that may lead to the movement of the tool up and down. Okay, so vibrations, more vibrations will be there. Okay. Now we have seen the consequences of tool wear. Now why tool wears? Okay, or why tool fails due to wear? And of course, here the concentration is mainly on tool failure. Okay, not only on wear. Now, how tool fails? Okay, why tool fails? That is the better question than why tool wears here. I will replace this. Why tool fails? Okay. So one reason is this: plastic deformation of the tool due to high temperature and large stress. So during cutting, obviously there is a temperature generation. So due to temperature generation, if it is high or temperature is there for a long time, then tool may plastically deform. Okay. And high temperature and a large stress. So at the same time, there is a good amount of force from the tool to the workpiece or between the tool and workpiece. So that will lead to the deformation at high temperatures. So first is plastic deformation. Second, mechanical breakage of tool. So tool may break due to large force and insufficient strength and toughness. Okay, if there is heavy force coming onto the cutting tool, so then obviously it may break because of high force. And the second is insufficient strength. Okay, if force is okay reasonably, we are applying sufficient force, not excessive force, but the tool is weak. Okay, there are some internal defects in the tool, so then also tool may fail. And if the toughness of the tool is less, okay, or otherwise brittleness is more, so then also it may not be able to absorb the forces and it will break mechanically. Now the third form is blunting of the cutting tool through a process of gradual wear. So gradually tool is losing some material from different areas. It may be at the tool tip or at the cutting edge. Okay. So or on the rake surface or on the flank surface, some amount of tool material is okay lost gradually. So why tool wears? There are different mechanisms of tool wear. Those things we'll discuss okay, in the coming slides. Our focus will be on tool wear mainly. Now first, for first thing, that is plastic deformation. Okay, if the failure is due to plastic deformation, so if you want to avoid that, you should have very good hot hardness for the cutting tool. If the cutting tool is hard enough at elevated temperatures, then it will not deform. Okay. Now second case, if you want to avoid mechanical breakage, tool should have good toughness. Third is blunting of cutting tool due to wear. So you should have good wear resistance. Now, three modes of tool failure. So one is excessive stress and mechanical chipping. Okay, whatever we have seen earlier, this is mainly mechanical breakage type, first one. Now next is thermal cracking and softening. So this is like plastic deformation related to that. And the third one is anyhow gradual wear. So for first case, this is due to mechanical properties. Tool doesn't have much strength, it doesn't have much toughness, etc. Okay, much hot hardness, okay, all these. Second is thermal cracking and softening due to high temperature generation. Okay, this is related to temperature. Third one is anyhow, as the name indicates, it is due to gradual wear. So you can see first case, cutting force becomes excessive and are dynamic, leading to brittle fracture. So if the cutting force is very high or it is changing too quickly, there is change in cutting force, it is not same continuously. So then also there will be vibrations and breakage of cutting tool. Second is obviously due to cutting temperature. Okay, so due to that it will lose its hardness. Now third, sliding of the chip along the rake face. Not only rake face, it can be along flank surface also. So chip is continuously sliding over the rake face or it is touching some portion of the flank surface. So then due to different mechanisms, what are those different mechanisms we will discuss. I am not explaining where right now because definitely we will see them in the coming slides. So these are the reasons. Sliding of the tool along the newly cut work surface, this is also there. Okay, tertiary deformation zone. Now among these, what is the most preferred mode of tool failure? As I told you, fracture and temperature failures are premature failures. Okay, so tool should not break or it should not deform. If it is happening, that means we have not manufactured the tool properly or we have not selected the tool material properly. Okay, so that is why the tool is failing. So it is premature failure. So this is not desirable. Now gradual wear is preferred because it leads to the longest possible use of the tool. So if the tool is failing due to wear, then you have very good tool life. Okay, if it is breaking, it may break very quickly, or the due to high temperature, it may deform very quickly. Now, where will this gradual wear occurs on the cutting tool? At what locations? So one is crater wear occurs on top rake surface. Okay, we'll see the figures. Now second is flank wear occurs on flank side of the cutting tool. So you can see here there are two locations. So here chip and tool interaction, okay, is there. At this location gradually tool will wear, okay, and here at this location there is interaction between workpiece and flank surface. Here also there can be gradual wear of the cutting tool. So these are the two locations. So here the main reason is the first case, that is chip tool. Friction between tool and chip. Okay, there is high friction, due to that temperature is also increasing. Okay, and sometimes chip is also sticking to the tool. Okay, and the chip is moving. So in that process, very minor portion, very minute portion of this tool material will also go with the chip. Okay, so in that fashion, gradually some crater wear may take place. Here between tool and the workpiece, so rubbing between tool and workpiece. So this flank surface is rubbing against the machined workpiece, a small amount here towards the tip. So due to that, the tool will wear. So crater wear on the top rake surface, flank wear on the flank side. So those are the locations: crater wear, flank wear, and main reasons also we have seen. And next is sources of gradual wear. Just a second. Hello, hello. Okay, just I'm a little busy. I'm in class. Okay, thank you. No, no, no. Okay, thank you. Bye. Okay. So I hope I am audible. Am I audible clearly?
Yes, sir.
Okay. Now sources of gradual wear. So, okay, we have seen the reasons to some extent, crater wear, flank wear, but now we will understand in detail what are the sources of the gradual wear. And before that, So types of wear. We have seen the locations. So based on the location only the name will come. Types of tool wear is, so here you can see worn cutting tool, principal locations and types of tool wear. So once the tool is worn, then you can see this kind of crater formed on the rake surface. So this is called crater wear on the rake surface. This is not exactly at the edge, just very small distance is there from the cutting edge, because this is where there is a high amount of interaction between chip and the cutting tool. Now another is flank wear. So flank wear you see from this region to up to this, okay, this black portion whatever is there, this is all flank wear. This is on the flank surface of the cutting tool. This starts from the cutting edge itself, okay, and it depends, okay, this length of the flank wear depends on depth of cut that you are using, okay. And towards the end of this flank wear you can see a notch wear. So notch is here at the end of this flank. Why this is happening means, so the chip is getting formed, okay, this is going in this direction. So at this location, the chip, sharp edge of the chip, okay, is continuously in contact with the flank surface and it is moving. It is like a blade, okay. So it is continuously cutting the tool. So at this location, you will have this type of a deep cut. So that is notch wear. And from tool tip, or tool tip will be there, you may have a nose radius also. So from that location along this auxiliary flank surface, there will be little bit of wear, just like flank wear, continuation of the flank wear only, okay. So and you can see this depends on the amount of feed that you are giving. So chip is coming like this. So some very small portion is there on the auxiliary flank surface. So this depends on the feed. If the feed is high, then this length will be more. If feed is less, this length will be less. And you can also see the bandwidth of the flank wear. Bandwidth is nothing but from here to here, average height. Okay, that is called the width of flank wear or the bandwidth of the flank wear. So these are the locations. Now if you see the crater wear, this is the real picture of the cutting tool, okay, after it is used for some time, okay, good amount of time. You can see here clearly, this is the crater, okay, just little away from the cutting edge. So here you can see the mechanism we have seen earlier. Due to friction, high temperature is getting generated and the chip is rubbing against the tool. So it is removing some portion of the material from the tool. So gradual wear, that is crater wear. And built up edge may also form, and if built up edge is forming, then it will take away some portion of the tool material with it. So that is also contributing to the tool wear, built up edge. Now if you try to understand this some terminology related to crater wear. So this is a tool. Crater, okay, is something like this. So chip contact length from this area, okay, from the tip of the cutting tool or from the cutting edge to this. So this is called chip contact length. So chip is in contact with the rake surface, but the contacting force is high towards this area, isn't it? Here it is very less because there is some gap here. Okay. And if you see the temperature during cutting process, high temperature may be around this area, okay, this region, just a little bit away from the cutting edge, not exactly at the cutting edge. So wherever the temperature is high, at that region, almost you will have the high crater depth. So we can see here there are some terminology. KF is crater front distance. So from the cutting edge till the starting of this crater, that is KF. Okay. So before any wear of the cutting tool, you see this okay, dotted line is given. And second is KB, crater width of the crater from the cutting edge, starting of the cutting edge to the ending of the crater. Km is crater center distance. So wherever the depth is highest, so that is the crater center. So from that point to the edge of the cutting tool, that is Km. Kt is the crater depth, maximum depth of the crater is Kt. These are some features that you will measure, okay, measurable parameters. So based on these parameters, you can define whether the tool has failed or not. Okay, we'll see exactly when you will say the tool is uh, failed. Okay, we will see them just after a few slides. Now coming to flank wear, it looks like okay this. You can see here very clearly. So this is all flank wear. So this is on principal flank. This is an auxiliary flank. Almost okay. This is the height. There will be slight variation in the height, so you will take the average height. And here you can clearly see one notch. Okay, towards the end of this flank wear. Now tool life criteria. Now we have understood okay how tool fails and what are the types of tool failure, that is crater wear and flank wear. Now when will you say that tool has failed due to wear? Okay. So one thing is if average flank wear is 0.3 mm. Okay. For a standard cutting tool, if it is flank wear is 0.3 mm, then you will say tool has failed. These are ISO standards. Okay, these are standards derived after a good amount of experimentation. Okay, after 0.3, it is not giving good results. Okay. Now maximum flank wear. If the maximum flank wear is 0.6 mm, so at least at one location, so flank wear is 0.6 mm. Then also you will say that tool has failed. Now coming to the depth of crater wear, so that is represented by KT. So if it is 0.06 mm plus 0.3 times of feed, if it is okay equal to that or just okay exceeds this value, then you will say that tool has failed. And of course, catastrophic failure, tool has just broken, okay, or suddenly it has lost its shape due to deformation. Then obviously we will say that tool has failed. So this is how you will define the tool life, or not a definition of tool life, due to gradual wear, okay, when you can say that tool has failed. Now, what is the mechanism involved in tool wear? First is abrasive wear. So, due to abrasion. Now, we'll see what is this. One by one, we'll see. Second is adhesion. Okay. So, obviously, adhesion, abrasion, they are between the workpiece and the tool or the chip. Chip is a part of a tool workpiece, which is removed, just removed. Now, diffusion wear and fatigue wear. Okay, these are the main mechanisms of tool wear. Now, let us see one by one. First is abrasive wear. So, here abrasive action of hard particles of work material. So, let us say you are turning a mild steel using some HSS tool. So, HSS is obviously harder. Sorry, harder than the mild steel, but even then there can be some impurities. There will be few impurities in the workpiece material. Okay, some very minor amount of silicon may be there. Okay, small amount of carbides may be there. Very small amount. Okay, so those are hard. So whenever the tool is interacting with those, so there will be some material removed from the tool. Now here the mechanism is like this. So whenever some hard material, okay, is interacting with some soft material, okay, at the microscopic level you will have some asperities. So this will come and hit this material, and this will be, okay, be removed, or this will be broken out. Okay, that is abrasive wear. Understand? So abrasive wear is the dominant cause of flank wear. So we have seen crater wear and flank wear. So flank wear happens mainly due to abrasive action. And why we are saying that that is abrasive, there are reasons for it. One thing is, on the surface of the workpiece, there can be some scaling. Okay, any fresh surface, it will try to oxidize. So immediately after machining, it is heated up, it is getting oxidized. Okay, oxidized means some hard layer has come. Now that is rubbing against the rake surface. And the chip also, sharp edge of the chip is also rubbing against the flank surface. So there will be abrasive action. Okay, because of this formed oxide or some scale is there. And of course, some impurities also are there within the workpiece material. So all these will cause the abrasive wear. And particularly this mechanism is predominantly present and contribute to the flank wear. A second type is, or the second type of mechanism for tool wear is adhesion wear. Adhesion takes place due to high pressure, localized fusion and rupturing. So we have seen in built up edge formation, so material is heated up It is highly pressurized. Pressure is nothing but due to compressive force. So, and localized fusion takes place between the rake surface and the chip. Okay, there will be some sticking action, and that will be now after sticking, the chip will anyhow try to move away. So, in that process, there will be a rupture between the rake surface and the chip, and very minor amount of tool material will go away with the chip. That is adhesion wear. So here there will be asperities. So this one material is sticking to the another material. So once, let us say this is a chip material, it is going out. So some portion of the tool material will also is also going with this chip. Okay, it is adhered to this. Now this is the main reason for crater wear. So on crater surface only we are getting very high temperature generation. So whenever temperature is high, okay, and pressure is high, then adhesion wear chances are more. So mainly this crater wear is caused due to adhesion. Now another type is diffusion wear. So here diffusion, loss of hardening atoms at tool chip boundary. So let us see a figure and understand. Tool chip boundary means this secondary interaction zone. So this is tool, this is chip. So obviously there can be some common chemical elements in both this tool and workpiece. Okay, let us say there is, of course, we will see the details also. So tool has tungsten, chromium, vanadium. Okay, and same tungsten, chromium, vanadium, and some ferrous. Okay, is there in the chip material. Okay. So at a high temperature, what will happen if the temperature is high? Okay, there is no gap between these. They are very closely also in contact. Okay, almost sticking to each other, and temperature is high. So at that time, the high amount of tungsten, chromium, vanadium, whatever is present, will try to go into the workpiece where very small amount of tungsten, chromium, vanadium are present, or whatever may be the element. Okay. So this is called a diffusion. So due to this, after some time, so tool is losing these hard elements like vanadium, chromium, tungsten. So then tool will become soft, and it will quickly lose the material here, soft material, because hard material is anyhow going through diffusion. So it will become soft and quickly lose its material in the form of crater wear. Okay, it can happen here also at tertiary zone, secondary zone also. Okay, so this is diffusion wear. This is also mainly at the crater wear location because temperature is high in this region. Okay, here of course there is no tool directly. Okay, so here very minor portion. And this may also happen, reverse is also possible. Okay, ferrous, very small amount of ferrous may be there in the cutting tool. So high amount of ferrous is there in the chip, it will try to come in. Okay, ferrous is coming in, tungsten is going out, chromium is going out, vanadium is going out, in that way. Okay, material is flowing from one region to another region. So wherever the density is low, so to that area, that material will go, try to go. Now next type of wear is fatigue wear. So here loading of asperities between work and the chip. Now what is it? So fatigue wear here. So let us say this is tool, this is a chip and this is tool. Chip is moving over the tool. So there will be irregularities at the microscopic level. So this irregularity, these okay will interact. Tool will not break immediately. If it is abrasive, very hard, then it will break. Otherwise, it may just slightly deform. Okay, just elastically deformed, and it will come back to its shape. Once this asperity goes out, it will again regain its shape. Okay. Now again after some time another asperity will come and hit this peak. Again, okay, it will bend and come back to its original position. So like that, there is a repetitive action. Okay, like this. So this will create fatigue in the tool material, okay, or this asperity. And after some time, whenever a new asperity comes from the chip and interacts with this tool, it may break now. Okay, repeated loading and unloading. So that is fatigue wear. You can see here, if you want to understand the mechanism, whenever it is coming and hitting this, what is happening? The region on this side of the asperity is subjected to high tension. Okay, it is just stretched out. So it is being compressed on this region. Okay, like that. So there will be repeated action of this kind of force on a particular asperity, and that will break after some time. So that is wear due to fatigue. Now temperature versus crater wear. So average tool chip interface temperature, if the temperature is increasing between chip and the tool, that is a secondary deformation zone. So gradually crater wear will increase. This is very obvious because crater wear is mainly due to adhesion and diffusion. So there will be more adhesion if the temperature is high, and there will be more diffusion also if the temperature is high. So hence crater wear will increase with the temperature. Okay, up to some temperature it is very gradual, but once it reaches certain high amount of temperature, then it will be very rapid. Okay. Apart from these major tool wear mechanisms, so what are major tool wear mechanisms? Adhesion, abrasion, diffusion, and fatigue. Those are the main. So there are few more mechanisms also involved in tool wear, but they are contributing. Their contribution is very less. So one type is oxide wear. So oxidation of tool material at elevated temperatures. So once the temperature is increasing, so obviously oxidation tendency of any material increases. So tool surface is getting oxidized. So oxidized means it is getting brittle, hard and brittle. Okay, hard, if it is becoming hard, okay, but if it is becoming brittle, then whenever it encounters some fluctuation in force, okay, there will be some chipping. And the next is plastic deformation due to excessive heat. Okay, so plastic deformation, we have seen this is one kind of failure. Plastic deformation, that is slightly different. Whatever we have seen earlier was sudden bending of the cutting tool, etc. That is plastic deformation. Here, plastic deformation of the cutting edge due to excessive wear, okay, or flank wear. Understand? Cutting edge is losing its shape, it is getting rounded off, okay, or irregular shape, it is going into irregular shape due to high amount of heat. So that will obviously contribute to the flank wear because okay, flank wear starts from the cutting edge. Okay, it includes the cutting edge also. Crater wear is slightly away from it. Now next is chemical decomposition through localized chemical reactions. Okay, so there can be chemical reactions within the tool or between the tool and the workpiece material or the chip material. This chemical reaction may be due to some cutting fluid you are providing. Cutting fluid will have some chemicals. Okay, those chemicals may react with the cutting tool. So due to that, some corrosion, okay, may take place. That is leading to chemical decomposition. And of course, we have seen this. Okay, oxide wear, same thing. So this is repeated actually by mistake. Now, tool wear versus cutting time. So consider a turning process. You have started the cutting, just started. So in the initial stages, okay, at the beginning time, there will be rapid tool wear. Tool wears very rapidly for some time. Okay. Now, after it reaches to some level of tool wear, there will be gradual tool wear, steady tool wear. Okay, slowly it will wear. Now again, after reaching to a certain high amount of tool wear, so there will be again rapid tool wear. Okay, and finally tool will fail. So first region is called break-in period. Now why this is happening? Anybody can give the reason? Why tool wear is rapid at the beginning? New tool. Okay. Any reason for this? If you understand, you can see this break-in period. So you can just take the analogy of one pencil. Okay, you sharpen the pencil. Okay, pencil is very sharp. Now, if you try to write with that pencil, so at the beginning, what will happen? Generally, there will be breakage or the chipping of that tip. Okay, at the very beginning, small amount, minor amount of breakage will be there. So once that breakage is there and you have used it for enough time, okay, just a small amount of time, now it will stabilize. Okay, for a long time you can write using that pencil without much difficulty. Now once it has become too blunt or too much of material is removed, then you will be getting very thick lines. Okay, and the pencil is wearing out very fast. Understand? It will become very blunt within no time. So same analogy you can use here also. At the beginning, there will be high stress concentrations on those sharp edges and tips. Okay, they are sharp, and whenever they are subjected to some force, there will be breakage due to the stress concentration. Okay, at the cutting edge, on the tool tip, etc. So once that small break-in period is over, so okay, it can be used for long time. Steady wear will be there. So once wear has become too much, okay, then the interaction between the chip and the tool will increase because now upper layer of the tool is removed, okay, and it is now no longer smooth also, okay. So there will be more interaction between the chip and the this zigzag area will be there here, okay. It is not sharp, so more sticking action, more friction, more heat will be there. So because of that, so it will be material will be removed fast. Upper surface is generally hard. If you are going inside, okay, its hardness will also decrease, okay, for any material in general, because upper surface is heat treated, okay, or it is subjected to heating and cooling from the surroundings, etc. But if you are going little deep, material is generally a little bit soft. So all these will contribute to the tool wear. So let us stop here. We'll discuss the measurement of tool wear in the next class. Okay. Yeah, I hope class is recorded. So anything to discuss in this course or in this topic, tool wear, tool life? Mainly we have discussed tool wear. Okay. Tool life anyhow we have defined to some extent based on the tool wear. We'll see more details in the next class. Any doubts here? Or any general thing you want to discuss regarding this course? Okay. So I'm asking these things in every class. If you have any genuine issue, you can bring it to my notice at any time. Okay, that's all for today. Thank you. Have a good day.
Thank you, sir.
Thank you, sir.